we're going to Google Darpa N3, and we're going to click on this link. This is the official DARPA website. N3, Next Generation Non-Surgical Neurotechnology. The Next Generation Non-Surgical Neurotechnology N3 program aims to develop high-performance, biodirectional, brain-machine interfaces for able-bodied service members. Such interfaces would be enabling technology for diverse national security applications, such as control of unmanned aerial vehicles and active cyber defense systems, or teaming with computer systems to successfully multitask during complex military missions. Whereas the most effective, state-of-the-art neural interfaces require surgery to implant electrodes into the brain, N3 technology would not require surgery and would be man-portable, thus making the technology accessible to a far wider population of potential users. Non-invasive neurotechnologies, such as the electroencephalogram and transcranial direct current stimulation, already exist, but do not offer the precision, signal resolution, and portability required for advanced applications by people working in real-world settings. The envisioned N3 technology breaks through the limitations of existing technology by delivering an integrated device that does not require surgical implantation, but has the precision to read from and write to 16 independent channels within a 16 cubic millimeters volume of neural tissue within 50 milliseconds. Each channel is capable of specifically interacting with submillimeter regions of the brain, with a spatial and temporal specificity that rivals existing invasive approaches. Individual devices can be combined to provide the ability to interface to multiple points in the brain at once, to enable future non-invasive brain-machine interfaces. N3 researchers are working to develop solutions that address challenges such as the physics of scattering and weakening of signals as they pass through skin, skull, and brain tissue, as well as designing algorithms for decoding and encoding neural signals that are represented by other modalities such as light, acoustic, or electromagnetic energy. Now let's go over here and search. Narrative networks. Why do people accept and act on certain kinds of information while dismissing others? Why are some narrative themes successful at building support for terrorism? What role can narratives play in causing and helping to treat post-traumatic stress disorder? These questions deal with the role narratives play in human psychology and sociology, and their answers have strategic implications for defense missions. DARPA launched the Narrative Networks program to understand how narratives influence human cognition and behavior and apply those findings in international security contexts. The program aims to address the factors that contribute to radicalization, violent social mobilization, insurgency, and terrorism among foreign populations, and to support conflict prevention and resolution, and effective communication and innovative PTSD treatments. Narratives may consolidate memory, shape emotions, cue heuristics and biases in judgment, and influence group distinctions. To determine their influence on cognitive functions requires a working theory of narratives, an understanding of what role they play in security contexts, and an examination of how to systematically analyze narratives and their psychological and neurobiological impact. Narrative Networks has 3 parallel tracks of research and development. Number 1, develop quantitative analytic tools to study narratives and their effects on human behavior and security contexts. Number 2, analyze the neurobiological impact of narratives on hormones and neurotransmitters, reward, processing, and emotion-cognition interaction. And number 3, develop models and simulations of narrative influence in social and environmental contexts. Develop sensors to determine their impact on individuals and groups, and suggest doctrinal modifications. Now let's go back to our Google page. And let's click on this link. Non-invasive brain stimulation at unprecedented resolution. In 2019, sitting in his office running computer simulations, Chaitanya, a PhD student in the Carnegie Mellon's Electrical and Computer Engineering department, noticed something that seemed too good to be true. The current patterns he had designed for focused, non-invasive stimulation of the brain seemed to be performing better than expected. It is well known that the skull disperses currents, reducing focus attained in the brain. Surprisingly, even when Chaitanya removed the skull in his simulations, the current pattern seemed as focused as with a skull. The skull became electrically transparent. I thought this was an error. These simulations, after all, take a lot of pieces to work together, and small errors can have big implications. To get these simulations, Chaitanya had hand-derived equations for how current in the brain can be described for an injected current pattern in the scalp. Chaitanya is a member of a team of researchers from Carnegie Mellon University who received a $11 million grant from the Defense Advanced Research Projects Agency, DARPA, to design a non-invasive neural interface that can be used as a wearable device for clinical applications and brain-machine interfacing. Despite his skepticism, Goswami discussed these results with fellow team member Matt Forcell, a postdoctoral student in the Electrical and Computer Engineering department who was doing physics experiments. Forcell was using Goswami's patterns to map the field generated in the brain using physics setups that mimic human tissue conductivity. Strikingly, I was observing the skull transparency experimentally, Forcell noted. Both got excited and published a co-authored work in the Journal of Neural Engineering. They also shared their observations with Vishal Jain, a neurobiologist, who along with Forcell was building a novel platform for testing non-invasive stimulation in alive brain slices. Non-invasive stimulation in alive brain slices. Jain's platform was designed to test and improve strategies like this. The three joined hands to test these strategies experimentally in Jain's platform. The results were a dramatic improvement over what clinicians do today. I immediately realized that this can have a deep practical impact on people's healthcare, said Jain. In the first phase of the DARPA award, on Jain's platform, the team successfully created a neural interface that is capable of recording and stimulating the brain's dynamic activity with high temporal and spatial resolution. This novel neural interface could enable unprecedented access to neural circuits to study brain function and dysfunction, as well as begin designing precise therapeutic interventions to treat neurological diseases and conditions such as epilepsy, pain, and depression. Now, in Phase 3, the team has initiated testing on human subjects. The project has made dramatic advances in stimulating large and small animals non-invasively, says Pulkit Grover, the Angel Jordan Professor of Electrical and Computer Engineering and lead PI. The resolution of our stimulation in both space and time is unprecedented. We are now translating these techniques to humans as well as collaborating with clinicians on testing them for treatments of neurological conditions. DARPA's Next Generation Non-Surgical Neural Technology N3 program aims to develop high-performance, biodirectional brain-machine interfaces. The team's techniques synthesize concepts in physics, biology, optimization, and artificial intelligence to obtain unprecedented resolution of non-invasive stimulation. So, DARPA's next generation non-surgical neurotechnology, N3, does not need a chip in your head. They use the air molecules around you.